So Felix is working on a very nice project, the Earth Data Lab, if I understood properly, which is also part of another project funded by the German Research Council or something like that, NFBI for Earth. And you will explain us how you implement DataCube and xarray with Julia. Am I correct?
Yes, I mean, I'm not going to talk about much about the implementation, but rather about the syntax and how to use it.
That's perfect. That's exactly what we want. Yeah, thanks a lot. So you can
Thanks,
start
Anne.
whenever you want.
Yeah, I'm going to talk about the Earth Data Lab and how to do large-scale computations in Julia. So just a bit of background. So this is currently, I'm employed by the NFDI for Earth project, which is the National Research Data Infrastructure for the Earth System Sciences in Germany. We focus on fair data access. We want to ignite a cultural shift in Earth system science towards openness and to also push people to actually use fair data. And we're planning on providing a one-stop access point for different data sets and user support for different questions around research data management for Earth system science. Then I wanted to quickly talk about why we're using Julia, or why I started using Julia. So there's always this talk about fast like C and easy like Python, and I think this might be a bit too high of an expectation, because if you want to have really high performance code, you also need to do things differently in Julia. But I really like that you have the scripting and high performance in the same language, so you can only speed up the parts that are actually bottlenecks of your code. And you have this multiple dispatch, which means that you select which function method is called depends on all input types, in contrast to Python, where it only depends on the first input type. And this makes it rather nice to combine different types, and you can better work with that. And I think it's also, I mean, in mathematics you have similar things, that it's like what actually happens is it depends on all input types. And what I also like as a scientist is that it makes it much easier to introspect into other people's code, because in Python, you always end up that some parts of your analysis is going to be written in C or C++, and then you wouldn't understand anymore what is actually going on. In Julia, most of the actual scientific code is written in Julia, and then so you can go much deeper into what is actually happening there. So now I want to start about the part about the Earth system, the Earth Data Lab. So first we activate our local environment. So this is basically similar to a virtual env in Python, and then we have to load the different packages that we're going to use. So this is the Earth Data Lab. Then statistics is the statistics standard library of Julia. Plots is a package for plotting. ESDL plots is a special package for plotting for these data cubes that we also wrote. Dates is the standard library for handling date types in Julia, and YAXArrays is basically the non-geo specific backend of Earth Data Lab. So it's basically, it stands for yet another xarray, and tries to give similar functionalities as xarrays. And then we can also use weighted online stats. So the idea behind the YAXArrays is that you use data larger than RAM, because we have a lot of data sets that are very, very large. I mean, you have to think about satellite data or climate models, weather data. So YAXArrays uses the disk arrays package in the background to only load the data that is really needed for your computation or for your plotting or whatever you want to do. We use chunks of the data. So all of the data is in small chunks. And then you can use either netcdf or the SAR or GDAL as a backend to load the data. And you can also load the data either from your local computer, as is here, with just using SAR, and then you just specify a path to some SAR file, or you can load it from some server. So this ESDC is now going to load the DataCube from a server here at the Max-Planck-Institute. But you could also specify this for different SAR files somewhere else. This is just a nice example of curated Earth system data sets that are all on the same grid, are all on the same temporal axis, which makes it much easier to work with. So here now we see that our data set has a longitude, so a spatial size of 1,440 elements by 720 elements, and 1,840 time steps on 69 variables, and has a total maximum size of 490 gigabytes. So this is not the actual size that is taken by the data set in memory or on your disk, but it's rather the size that that you would get multiplying all dimension lengths by the size of the element type of your data cube. But so this is just a lazy representation of your data, and this is not loaded yet. This is just we know that, so this is basically a pointer to a data set, and it grabs some metadata from the SAR file, and then it knows, okay, what is actually in there and what would I expect if I would load it. Now we can do also lazy subsets. So if we run this is also immediately executed. So here you can subset the cube on the region Europe, and then you can also specify time range, and you can restrict certain variables. And now we can just plot the air temperature for Jena, and see that we get a nice seasonality here, and then but you see that the range is between 270 to 300 degrees, so it's in Kelvin. And now we can just do a computation on every element of our cube. So we can just do this map on this. So this is on the subset, only on the air temperature, and then we just subtract 273 to convert to Celsius from Kelvin. And then you get a cube which has the same axis sizes as the cube we started with. But now after we plotted it, let me plot this again. So now you see the range is between -10 and 25 for the mean air temperature per day. So this was a computation on every element, but we can also do computations along certain named axes. So as an example, we can just compute the maximal range of the values. So it's the 95th to 5th percentile to get an estimate about what is the range of values we're looking at. And to do that, we define this p-range function, which has always the structure that this is the output that I'm expecting. This is the input that I get from the cube, and then I can have certain other extra variables. So you can have, and then you define the function inside here, and you can use the whole Julia ecosystem to define these inner functions. And then if you want to apply this, so here we're just applying it to Italy, but we can use this mapcube function, where you just state the function you want to apply, the data set you want to apply. Then you have this parameter, which is going to be put into the parameters here. So this 0.05 is going to be the threshold here. And then you define the input dimensions. And here you can specify, I'm going to apply this on the time axis. So I want to have the temporal range. So and the output dimensions are empty because I'm doing a reduction in time, because I'm getting, for every time series I put in, I'm just returning one value. And so if we now run this, we see that we lost the time axis basically as an axis. So we reduced the whole time series to one value, and then we could plot this with this plot map and then see these value ranges across Italy. And we can also do moving window computations. So if you want to have a moving window in space or in time, you can basically, now we can just smooth the results we got by applying this moving mean. And here we just going to put this is the output. So we're going to use the input, compute the mean, and then put this into the output. And here this little dot this is called broadcasting. So we're applying this on every element of X out. So it's just replace here. It just means we're replacing the output by the mean of the input. And now you apply this again with the mapcube function, but you will specify the input dimensions differently, because here now you say, okay, the input dimension is not just the latitude, but it's a moving window across the latitude. And this 1, 1 means one step before and one step after every element you put in. So it's basically, and then because we're doing it for the latitude and for the longitude, you get a 3x3 matrix around your element you're computing. And you could also play around with these values. So you could basically, for time series applications, you could say, okay, I don't want to use time steps that are in the future of the step I'm currently computing. So you can set the before step to 0 so that this wouldn't happen. And now if we run this, we get a smoothed image of the values we computed before. but you see there's a few missing values on the edge, because basically if it's on the edge, it doesn't know whether it's so it's basically filled with missing values on the near next to the edge of your image, and so the mean of the first two rows and columns are going to be also missing. Therefore, you have this gray bar. But you could then check for missing values and compute only the mean on the non-missing values to also get a little bit less smoothed image on the pixel on the side, but still get a value. Then if you want to do a bit more complicated stuff, you can also use the cube axis as cubes as well. So here we're using the and put them then into the inner function. And you could also combine multiple cubes. So for your computation. Here we're going to just use the Lomskagel, which is is similar to a Fourier periodogram, but it works on irregular time series. And I'm not going to go into detail what's actually computing, but to do that, you would need to know your time steps. So you need the information of your time axis in your inner function. And to do this, we have again this x out, x in, and then times. So this is the time axis. And then for the application, we say, okay, the input dimension is the time. So I want to apply this on every time series. And then the output dimension is a categorical axis where which I just call Lomskagel, and which has different values. So it's the number of frequencies, the period with maximal power, and the maximal power, which are just outputs of the Lomskagel periodogram. So you see here that basically this matches the number of outputs of the inner function. And then we extract the time axis of our input cube with this getAxis function. And then as output, we use this categorical axis we defined. And then you can apply this again on, so you define the function that you're applying, and then as input, you don't have not one cube, but you have a tuple of these two cubes. And as input dimensions, you then also have a tuple of input dimensions. And then if you compute this, you get you get a data cube which has then these three axes. So the time axis is converted into this new Lomskagel axis. And if you so the idea here is also that I mean, now for the example, I restricted this all to the Celsius cube. But our first input cube had 69 variables. So if you would do this on a large cube, it would do the same computations. And then you would have a fourth axis here, which is just the variables. And then it would of course take some more time, but it would be very easy to just say, okay, I want to do the same computation on not only on the temperature, but on other variables as well. Then you can also combine the data cube with with reference polygons. So here we are with this cube from shape function, we are constructing a data cube from a shapefile, which has the same longitude and latitude grid as the input cube that we're providing, so as the reference cube. And we can also use a label symbol. So we can say, okay, which of the columns in the database of the shapefile should be used as labels for my polygons here. And so you see here, so the labels are always represented as numbers inside of the data cube, or inside of this data cube that you get from cube from shape. And then you have a mapping from which number corresponds to which name label. And so with that, we can construct tables. Wait, I need to run this first. I don't like, I wanted to show. So this is just the table. So this cube table gives a table representation for the, which combines the Celsius cube as a TR. So it's always, this is the column name, and then this is the input. And I can just show you. So this table is now an iterator over this these two tables with, and it has these fields TR, country, longitude, latitude, and time. And now we can apply online statistics. So here we are computing a weighted mean of the on this table that we just produced on the air temperature. We're weighting by the cosine of the latitude, so it's basically so we adjust for the fact that the pixels are getting smaller in northern latitudes, and we are sorting this, or yes, grouping this by the country and by the months of the input time. And now takes some time, but now I can have a look into the questions. So the plotting is based on Matplotlib, because I'm using the plots package, which has Matplotlib as a backend, but there can be other plotting packages. You don't need to provide the exact latitude and longitude values. You can just, it's taking the nearest point in your axis as the values. Now this is done. So you see here we have a new data cube with a label element for every country and a category of another axis for these 12 elements, which will just be the months. And then now we can tidy this up a bit and just rename these axes. And now we can just plot the bar plots of the mean air temperature per month per country for different countries. And so this was now all in Julia, but sometimes you have packages that you can't find in Julia, or you have your analysis already in Python and you want to still do these analysis, right? And then you can use PyCall package, or you could do something similar with the rcall package for R. And so you can use the Python functions in your inner functions and let the data be handled by YAXArrays. And to do that, we're using this PyCall, and then we can import the SciPy and the image package from SciPy, and now we have the SciPy and the image package available, and then we can write a Gaussian filter, just as an example, from in the same structure as the other internal functions that we used for YAXArrays, but now here we're using this SciPy and the image. And now we're just subsetting again the value. So this is now GPP in Jena, and so we have give it a latitude, longitude, a time range, a variable name, just to get one time series. And then we can just smooth this going from an input dimension of time to an input dimension of time again. So we get the same size of the data cube. This is now taking a time. I don't. And so then we can just plot it, and then I'm not going to run it now, but earlier you can just to see that you can also do this with, I mean, this was the example for Jena, but now you could do this and apply the function over the whole Europe data set. And what is also nice is that YAXArrays takes care of the distributing of your computations. So if you have multiple processes, either on your computer, or you can use distributed on multiple computers, or you can also use it with cluster managers like Slurm. You can just first load the distributed standard library, then add some workers. And then you have to activate the local environment again on every worker and make sure that the functions you want to apply are available. And now you can just run your analysis either multi-threaded or or parallelized on the data. Yeah. That was a small introduction into YAXArrays and how we use it for data handling in Julia. And now I'm happy to answer your questions.
So I think you have